Okay, so this is our chapter 18, and we'll get into coordinate measuring machines. So coordinate measuring machines, so we're getting into coordinates. So you have to understand your X, Y, and Z axis, okay? And we also call them CMM. So that's coordinate measuring machine. And they're extremely powerful metrological instruments, okay? Metrology, again, we use these instruments to measure. So a bridge type CMM is shown here, okay? This is a pretty big measuring instrument, and you can see the probe right there. And we call this a CMM. It's always connected to the software. So here you can see a little monitor, and then that's the printer for the printouts. And they can locate coordinates, again your X, Y, and Z axis. And you can do it on the three-dimensional structures. So that's your 3D. And we can do that at the same time. They measure the orthogonal measurements. Orthogonal, again, is your review. Okay, that's just we're measuring involving the right angles. And they're, again, as a review, they're totally statistically independent. So this is just an example of a bridge, okay, because it looks like a bridge. See the probe is. So we call that a bridge type CMM, a coordinate measuring machine. So when a computer is added to a CMM, you can automatically perform complex analysis, and also you can learn the measurement routines to compare to its specs, okay, your specifications. So complex workpiece, they can be dimensionally evaluated because we're getting into 3D. And because of these machines, we can do it with precision and also with high speed. The data can be stored because it's connected to the computer for later analysis. Then we can take it back out and do comparison. So the greater the complexity of the piece, the greater the benefits from a CMM, okay? So these coordinate measuring machines can definitely increase, again, I'm going to point it out here, your speed and accuracy, okay, of the inspection process. Okay, so let's get into background. So the very first one is the development of CMM. So we're looking at the same person, your Johansen and then Roth. So they wrote about machines, and they're pretty crazy about machines that could measure in 3 axes, okay? Again, your X, Y, and then Z. So in 1940, the Atomic Energy Commission first recognized the potential of these CMMs, and at that time, they were dealing with the computer technology, okay, putting with the CMM so that we can increase the speed and accuracy. So in 1960, CMM became a very powerful tool, and manufacturers, they wanted. And with microprocessor power in computing, and they also have the processing data. So CMM becomes influential in measurements, okay? So metrology is the study of measurements. Alright, next one is the role of coordinate measuring machine. So what do we use for CMM? They play an important role in industries, again, aerospace, automotive, electronics, food, healthcare, paper, pharmaceutical, plastic, research and development, and semiconductors. So CMMs are used for parts with complex geometry and assemblies. Okay? And inspection time can be reduced. That's why we use CMM. and we can reduce on the order of 80% to 90%. So that's pretty good figure. CM are well suited for short production runs. Okay, multiple features, flexibility, and high unit cost, and the production interruption. So these are the roles for coordinated measuring machine. Again, the point is complex geometry and assembly. Okay, so when you take a look at here, CMM work well for complex part assembly. So this is in the lab, okay, for manufacturing lab, and it's just doing inspection of the entire product, which is your motorcycle here. Now we'll get into types of CMM. We have many different types. So here you can see 5 of them. So basic CMM. Okay, they have 3 perpendicular axes because we can measure all 3. So each axis is fitted with a precision scale, measuring device, or transducer that continually record the displacement of each carriage from a fixed reference. So there are 5 basic configurations, and we use them most frequently. They are, the very first one is a cantilever, and the second one is your bridge, column, horizontal arm, and gantry. So again, the key points here, we have 5, okay, often used, and the CMMs, again, hitting the 3 axes, X, Y, and Z. And we already knew X, Y, and Z, they are perpendicular to each other, right? Totally orthogonal. And then each axis is going to be fitted with a precision scale and a measuring device, okay? Or we use a transducer. So what does it do? This transducer is going to continuously record the displacement, okay? That's your measurement of each carriage, right? From a fixed, again, reference. You always need a reference in measuring. We have done so many chapters again and again. Your calibration, your instrument comes with the error. You are the error. Okay? Every measurement system, they have a reference point. Alignment matters. Okay, you have to know your unit. Otherwise, you don't know how to transfer your data to somebody. And they need to reproduce, okay, what you report. So therefore, units are so important. There are 2 of them, major, LUSI, not used in America, and your English, okay, we call that British. So it depends on where you're going to be working. They will be calling either British or English. And come back here, CMM, dealing with the coordinate measuring machines. They are machines because they have to deal with big products, complex assemblies. Okay, now let's go. Next one. The very first one is cantilever type. Looks like this. This one is your fixed table. This one is your moving table. Okay, so you can see right here your x-axis is completely moving back and forth. This one can move. That one can move. Okay. Here is you have your base right here, or the table is completely fixed. So in this type, a vertical probe, those are your probes, okay? Move in the z-axis, which is this little guy right there, okay? So here I can draw down for you, and get that way, and then this way, and that way, okay? So by looking at it, you should be able to see that now. And that probe is carried by a cantilever arm, right? That moves in the y direction, so which is this one. Okay, now we tilt it, so z is now right here. I'm gonna write that down for you. Now right here, axis like this. Okay, we usually look our eyes. Okay, when we draw it on the 2D paper, we usually look at that this way. So don't, when you draw, you draw this way. Okay, so here is your x again, and this is your y, and then this is your z when we draw on the paper. but in a 3D space, Z is right there. But if you are with people who don't follow the rules, okay, scientific rules, you're gonna be seeing like they will be drawing that and then this, and somebody gotta fix it when they transfer the data, okay? But anyway, the work area can be easily accessed. It doesn't take up a big floor space at all by using these machines, so it's pretty convenient, and that's the reason why we can speed up, okay? Alright, the next one is a bridge type. We call it bridge because it does look like a bridge. So here's the most popular type. People like to use it because, again, why is it popular? Because it's easy to use, okay? And then the machine has a moving bridge. So, and it has a support, okay, for the outer ends of your y-axis beam on the base. That's Z. Try to draw this again for you. Yeah, like that. So let's just see. Then your X, then your Y. And the bridge construction adds rigidity to the machine, so you can see a very solid, right, and stable structure. So that's pretty good machine. That's why people love to use this type of CMM. A fixed bridge type, that's what this one here has, a bridge fixed to the base right there. See, here is your bridge and it is fixed. So you can hold it if that's totally fixed right there and you can't move. You've got a fixed bridge type. And this setup can eliminate potential tracking problem of the standard bridge CMM. And it also provides superior accuracy. And therefore we use it for gauge room applications and production inspection. And here, look at the structure, they're a little bit different from the fixed bridge because this one has moving. Right there, see, it's completely moving. Here, so that's again Z, your Y, and then your X. Sometimes you can also use, like, if you twist it like this, you can also use this as an X, okay? But anyhow, this is your Y. And this is your L-shaped bridge type. A bit different. But again, you can say you can move, okay, all of this. The arrow is pretty small, so anyway, you can move in all three axes. And for fixed type, you can move only this area, see? So you can trace these arrows right there in the handout. So when you're looking at the handout and if you see the picture is really small, make sure you can zoom it out, okay? So zoom out, zoom in, so that way you can adjust the picture and can be able to see this little arrow right there. They're just showing you the movement of the machine part. The column type looks like that. Here are your three axes, and it looks like a jig bar, and it's called as a universal measuring machine. It provides exceptional rigidity and accuracy. They use the word exceptional because it is exceptional, and they are used again in gauge room, okay? Because the reliability is pretty good. The machine with the best reliability always go into the gauge room because we can use them as standard. The horizontal arm type, a little bit different. The probes, okay, they're very different. So this type, we call it a layout machine. Those of you who are in motion class, oh my gosh, I have to teach you so many times about the layout. Anyway, layout, always remember 3D, okay? Layout machine we call them, and it has a moving arm, and the probe is carried along the y-axis, and it provides a large unobstructed area. It's really perfect for large work pieces like automotive dies, things like that. And the fixed arm type has this one right here, okay, has a probe fixed to the y-axis with moving walkable walk table and y-axis. So here, your x, this one is your x, that's your horizontal, and this is your y right here, and then this is your z. So this type again, the probe is carried along the y-axis, right? So going that way. And here the same thing. You can see this little arrow right there. So I'm going to draw that out for you. And this actually is turning like that. See right there? And that's your x-axis. And then your y-axis should write this nicely. That's the y-axis is here. And then the z-axis is going to be right up there. And here we draw the same thing. Your x and then your y here. Then your z. Those of you who are in 3D shouldn't have any kind of issue finding the axis, okay? And also it depends on the manufacturer, and they will definitely tell you which direction they're calling x-axis and y-axis, okay? And z-axis. So you'll have to follow the instrument manual, because some of the manufacturer, again, they do not follow the scientific rule. They will manufacture and then just put whatever. So anyway, this machine type, the horizontal arm type, actually the probe moves along the y-axis is your key point. Okay, so I'm going to point this out again. Along the y-axis, along the y-axis, and along the y-axis, that way. And we use it for large work pieces, especially in the automotive industry, they use this. Gantry. Gantry looks like this. So the support of the workpiece is completely independent. That's why you can see the base right here. Okay, again, here is your Z, and this is your X, and then that is your Y. You always get the Z-axis, and you will have a confusion between your Y and then your X-axis, right? And try to read this slowly and take it in slowly. Take it into your brain slowly. Alright. So again, the point right here, the support isn't there. Why? Because it is independent. So both of which are overhead, supported by 4 vertical columns right there, rising directly from the floor. So these are your columns. There are 4 of them to stabilize the probe right here, yeah? So here again, the five most common variations of the basic types. They have differences that enhance the convenience and efficiency. We're hitting again, we make the machine. Machines are technology. Why do we have to enhance the technology? Because we want to improve convenience and efficiency. Because we're dealing with many different kinds of situations. Therefore, you need many different kinds of CMM, right, to satisfy these situations. Modes of operation. CMM can be divided into following categories. We have 1, 2, and 3. The very first one is manual. Second one is manual computer assisted. The third one is motorized computer assisted. So the manual mode is just a free floating probe. Okay, here that's we call this little thing right there, the end of this machine, a probe, which operator moves along the machine 3-axis to establish the contact with the part being measured. Okay. The manual computer assisted is the second mode of operation, and you have electronic displays are added to do zero setting, your calibration, sign change, direction, inch your unit, decimal inch your unit, SI conversion your unit, and your data print out your records. Okay. The next one is your motorized computer assisted. It uses a joystick. So this machine is your third mode of operation. To drive the machine to bring probe sensor into contact with the workpiece. Okay. The direction into the future for the machines are heavily based on the sensor because we're making a lot of them smart. Okay. The only way to be smart is algorithms. Another one is the probe or the sensors. Can sense it and knows it. Pair it with a database, yeah, and make it intelligent. Alright, the next one. So this is another mode of operation, and we call that direct computer controlled. It's DCC, fully programmable. And this type of CNN uses the taught locations of your CAD data to determine where the probe sensor contacts the workpiece, right? And then collect the data point and generate an output report. So in our basic lab, you already know what the data points are, okay? The points that you measure the data is called data point on the object you're measuring. So here, when we actually do metrology in manufacturing, you're measuring bigger parts of your product. When you hit the complex assembly like car and airplanes, train, okay, you've got to get into complex, all right, data points. But you can do it because the procedure is the same. When you have to deal with so many data, you have to go into details and you have to be detail oriented. And university courses are training you to do all of that in 4 years. Okay. So don't just go for easy course and try to get a grade in an easy way, because nothing is easy. Alright, in university, so make sure you study. Okay, there's no way out but to study. Alright, the term computer again includes your computer microprocessors and your programs, alright, programmable controllers. We have to drive the machine that we want to use. So in this case, it's your CMM, and we use the location of your CAD data. Sometimes I forgot, some of the students don't know, okay, so because they haven't learned. So anyway, CAD is nothing but just another computer aided design, and you can do 2D, and then you can also do 3D models of your real world product, okay, like this, before they ever manufactured. So with 3D CAD, you can share, review, stimulate, and alter, okay, whatever design you're doing. Okay, now let's get into types of probe. So here in this machine, this is your bridge. Pretty big machine, huh? Completely computerized. So mode of operation is definitely with the computer. And here you can see it's probe. So all CMM consists of a probe and a way to move, alright, along the 3-axis. So we go back to our 3-axis again, like that. Now you should be able to know, and you can move right here at Y-axis, and that's your Z, and then this is your X, okay? This imaginary axis, when you look at it, you should be able to know that immediately, yeah? So practice that. So all CMM consists again a probe, and then they can move along that 3-axis relative to the workpiece. So in CMM, sensing the element is called the head, and the probe is the heart of your CMM operation, because that's a critical. Gonna draw this again for you here, okay? Because without this, it's just worthless machine. And this is the most expensive, the most critical point right there for measurement. That's why they use it as a heart. Alright, and sensing element again, right there. The CMM is very sensitive sensor. So CMM is placed in an orthogonal array. Every time you see this one, that's your right angle. And there are a variety of probe types and designs. You need it because you have to measure different kinds of stuff. And probes gonna fall into 2 categories. One you're gonna touch, contact. The other one you're not gonna touch, non-contact probes. I love machines. I like all this software application. Oh my gosh, so good to play. Okay, contact probes. They look like this, and the most common type of probe used to CMM because it's easier to manufacture contact probes than non-contact probes. Non-contact more expensive. So for example, touch trigger probe, analog scanning probe. They're called the contact because they have contact with the part. Okay, this little one right here. Where's my pen? Here. This one. And they can scan along the surface of the part being measured. And we can read along, that's your body, and that's your module, part of your body. And then you can change that. Here is it's just a stylus, right? This is your point where the sensor is. In this example, they call it M2, but it's just a stylus. The standard force black, medium, force gray, extended force brown. That's just the, particularly this pattern, US pattern right here. And it doesn't really matter. I'm just telling you what type of this tool is. This is your front ring, and that's your color-coded protection cover. It's not necessary. The only thing that is necessary is your stylus, and then your probe head and the sensor. And this is where your spanner location is, and this is important alignment marks. You should be able to know this if you look at it. And then here is your magnetically held countermagnetic coupling, okay, for your movement. For measurement alignment, so important. The point of contact with the part, very important, because without that you can't be able to measure. Alright, the next one is a touch triggered probe. Touch trigger is nothing but when you start to measure, as soon as you have a contact, it's going to trigger the measurement. And it has a head with a LED light, okay, which is just a signal, okay, telling you, oh, I'm start measuring, which can be triggered when it contacts with a part. The analog probes are used to measure contour surfaces, okay, like the turbine blade and things like that. Contour is pretty. See, look at this little one right here. I tried to give you a water bottle with a lot of grooves, and it's just like that. And I have only one machine with it. I don't know if it's working or not. I'm trying to fix it, so it'll be ready for next semester that we can do at least a one surface measuring. But in the future, I'll try to get different machine from by making money. Okay, so pray for the grant to come through. We can be able to get some money. All right, next one. This is a low trigger force, high sensitivity touch probe. So you can see right here, see this little probe sensor right there, how sensitive that is. So this is your part being measured. So in our basic lab, you have like a big instrument defect instrument with all the errors that there is in the world, and it'd be very difficult, right? Even we have this like container like that, and you have a hard time trying to measure, hard time to report what you're measuring, right? Anyway, for real world, if you want to know the real world is nothing but hard work, a lot of repetitions. And trying to measure this little one, how are you going to measure? You can measure with micrometer, you can measure with vernier, you can measure with height gauge, you can measure with gauges at all. So therefore, this type of part, how to measure, we have to measure by using probe and CMMs, okay? Alright, so the non-contact probes, we use a laser because you can't use a tip like this. So we use a laser light non-contact and a video probe scanning, okay, with a video. Back to our low trigger force probe right here. This is just like they're very sensitive. That's why when you look at the probe head, it's very tiny little, even looking like a little needle, yeah? And that's the reason why you can be able to measure these flexible things with like a rubber O-ring in there. And that's another type of probe. Okay, continue. So touch probe assembly consists of 3 components, your probe head, and then your probe, and then your stylus, okay? And you can see many different kinds of probe right there. So probe is attached to the machine quill by means of a head, and a variety of heads are available. We have different kinds of heads right there. And some of them are totally motorized, and some carry 2 or more styli. Yeah, here are just ones. Here are 1, 2, and here are the third one right there. This guy has 2, yeah. So I can point it out for you here, and then here. So the first stylus is here, second stylus is here. Here is your first stylus, second one, and then the third one here. So some probe head is carrying 1 or more, right, styli. And in this picture, you can see many more. See, like 1, 2, 3, 4, 5. Here we have 1, 2, 3, 4, 5, and it can rotate in 3 different axes. Extensions, they're common and they're added to the ProHead for extended reach of positioning. So you can see right here that's completely extended. You can go see there are groups right there, right? So you can go inside to measure this part. And here this is just a cartoon. You can see the probe head, and then you have different. This is just a probe body attached to your stylus. And why do we have to use a different stylus and extensions like that? So this part, so I'm going to draw that for you, will come into here, yeah? So if you put this extension here, it got longer. So your stylus is going to come right there. And then if you put this, It's gonna be like medium height right there. Anyway, you can change the length of the probe by using extensions. Probe head right here. You can rotate it manually, you can rotate it automatically. Okay. This ProHead is about, for this example, 7.5-degree increments for increased measurement flexibility. Here we're measuring the surface of this part. So we use these things. So when you manufacture parts like this, you definitely need to do inspection. So inspection is my field, which is called a quality assurance and quality control, quality system. And you've got to do this job, okay? And metrology is right in that area if you want to go into quality line. And we have many different kinds of profession in manufacturing. But for quality, you might need to study at least masters if you don't have certification. If you don't want to continue to study, then you can take different certification from a group called ESQ. Okay, it's a completely accepted organization for certification. And the conference we went last week, okay, ADME also. Here you guys call it ADME, we call it ATMAE. Anyways, this group also certify you in Six Sigma, but not as strong as ESQ. So definitely recommend ESQ if you want to go into this kind of line without going to graduate school. Alright, next one is your stylus. You can change the stylus, you already know about it. You can also program that, okay, to automatically do the inspection routine. So you can save time, you don't have to change it manually. So the correct stylus, you can program it to change according to the part that you're measuring. So by giving automation, okay, and programmed to the machine to choose the stylus, you're increasing the accuracy because you can reduce a human error, okay, of manually switching the stylus. So here we have, if you pay attention to the picture, you can see 1, 2, 3. Okay, this one empty. So anyway, you can program the machine to change that. Calibration. Every instrument we've got, we have to do calibration so that we know the instrument is definitely doing its job, which is measuring correctly. So before you do a measurement, you have to do a calibration to check, to clean, okay, and to enhance the accuracy. So the accuracy in touch probe, it depends on using a good probing technique, okay, just to be careful. Careful with the alignment, careful with the reference. Because probe style selection, they can, if you are careful, you can reduce the error. So go slow and go little by little, okay? Don't do anything in haste. When you deal with measurement, you have to have patience, real patience. Everything in the lab, you have to have patience and details. Okay, so important. These two things, patience and details, are pretty good, okay, for everybody who is in the lab, measuring something or inspecting something or checking something. Alright, and here you can see a table, and that's just showing you the maximizing probe accuracy. Just follow these good practices right there. The first one is use a short stylus diff to minimize bending. Use the lowest probing force that will not cause a false trigger. Calibrate to a known standard. We do that all the time, right? Your spear, ring gauge, or gauge blocks. In our basic lab, we use the gauge blocks. And then probe measurements should be made perpendicular to the workpiece, okay? 90-degree perpendicular. Ensure that the probe tip, not the shank, is making contact with the part. So therefore, the probe tip is so important. And this is the one you want to be in contact with your part. And you have to make sure the stylus is not loose. Most of the stylus are attached to the probe head right there, often with a screw, okay? So make sure you set up your CMM in a correct way with the correct stylus. So if you follow these practices, then you should be fine. Non-contact. Alright, non-contact type, we use it in inspection, circuit boards, complicated boards. Measuring a clay or wax model, you don't want to touch it. You know? Prevent deformation of object being measured by stylus force. We don't want the part to be touched with, even with the probe, okay, because it's gonna deviate the measurement. So one type of non-contact probe, we use laser, again light scan, and this is this one right here, okay. This is your laser scan, and it is your non-contact probe. The laser probe projects a light beam on the surface of a part. So this one is what it's measuring right now in the picture. And the distance from the point of measurement, we call that standoff. So the original objective of the non-contact probe was the measurement of soft or fragile surfaces like this one, wax. This is a totally wax prototype, and they're prototyping an automobile, a car. Okay. So however, the great speeds at which it can operate make it valuable for inspection, in which a large number of measurements must be taken, like a digitizing complex profile. So anyway, all you have to understand about the non-contact type, we have to do the non-contact type because we don't want to disturb the part, okay? And usually soft part like clay, expensive, right? Clay that you do measuring the museum artifact uses scanning, because you don't want to mess up with the very, very ancient and delicate and old objects. So when you do precision measurement, you use this type of non-contact type probe using laser, and also especially to prevent deformation. Okay, complex object like circuit boards. So we use a non-contact type probe. So when you take a look at this picture, you can see another type of non-contact probe is your video probe. So here she is using a video probe, and it totally relies on a high resolution image of the part. And we try to do a video on ours basic look is not video, it's just a picture that we're using, but similar to that. However, we have a disadvantage because the software that we're using is a really basic one, and it doesn't give you the correct measuring capability, because Microsoft Word doesn't have it. But iPhone has an application to measure, so you do have a video non-contact type kind of machine CMM integrated into the application of your iPhone. So people with iPhone can download. Sometimes it's already there. Okay, there's something called Measure. That's the kind of the video probe that you can do. Okay, because you can definitely measure by using a digital program. Alright, the next one is a direct computer control. So these are huge DCC right there. So computers are now widely used to control because they're very reliable, and we control the processes by using computer to increase again versatility, convenience as always, and of course reliability of production. So DCC is only applicable to motorized, alright, CMM, not the manual ones. And they're like computer CNC. Okay, what you're learning right now with Dr. Wyatt, I believe. I don't know who is teaching. I think he is teaching. So like computer numerically controlled machine tools. So both control and measure cycle are handled by the computer. So that's a direct computer control DCC of manufacturing is referred to as a CAM, or computer assisted manufacturing. Okay, so make sure those of you who haven't taken CNC, okay, CAM, CAD, don't confuse with all your acronyms. Try to know which one is what. Okay, so the program for the CC machine, they have three components, and we have move, they're all commands, move, measurement, and formatting. So for move commands, they direct the probe to the data collection points. We have already done our basic labs about the measurement points. So here, when we use a machine, we can program the machine to take measurement of particular points, okay? On the measurement commands, we compare the distance traveled with a standard built into the machine for that axis. For formatting, we translate the data into a form for display or input. So here, what we're trying to tell you is for the DCC, it's your direct computer control. We're gonna control, okay, our machine by using programs, and we program three different things: to move, to measure, and to format. Okay, to move, moving the probe to the points of measurements. To measure, okay, we're comparing our distance traveled with a standard, alright, built into the machine for that of your axis. And then formatting commands, we're going to translate the data again into a form for display or a printout. Okay, so this is just a short video from YouTube. I try not to put a lot of video because when we export the video, it does mess up, okay? But it's good to have sometimes, boring lecture. Anyway, so let's take a break. I'm gonna go and drink some water and you can watch this one. I just trying to tell you the definition of ANC, CNC, and DNC. Okay, I'm back. So anyway, this is for those students who haven't taken CNC. Okay, so the previous video is just showing you what CNC is. Alright, so let's continue. CMM software. Again, software is just a computer program you can use with our machine CMMs. So that's just a machine programming or software systems. It's going to enable your CMM to accuracy, precision, and speed. So these are the three criteria we're looking for our machine to do for us. Technology is again nothing but things that we can't be able to do. We're making the machine to do it for us. So that way we can reduce the human errors. Because human is very intelligent, but also we cannot constantly rely on human capabilities because we have emotional changes. And our performance depend on our day. Okay, so if you have a bad day, your performance is going down, so you can't really get a constant performance out of human. So that's the reason why in manufacturing we have to use the machines, because we can rely on them. Okay, we cannot rely on the human capabilities, therefore we have technologies. So CMM software are menu driven again, therefore operator can operate it. An operator got to input what he wants or what she wants, the desired end results to the machine, so the machine will do it for you. Software again is very good. I love software, I love machine, I love robots. Pretty good. And software is nothing but it's going to allow the operator, who are us, to interface with a computer very quickly and efficiently. So if you have your computer, it's programmed, right? And you have to speak to it, and that's where software comes in. So you translate what you think to your hands, and your hands type something in. Okay, that's usually what you can read, which is your language in English or in something. You put on your keyboard. Keyboard is going to translate and going to touch up the code. The computer is going to read in 0 and 1 or different kinds of code. Okay, and we'll send that information again. We're using the little photons, little particles right there. Don't forget that they control the entire universe, not us. We are one of the things that they have created. So anyway, alright. So anyway, what we're trying to do, use the CMM software to communicate with the machine for accuracy, precision, and speed. Also to drive it, with the result we wanted to do. So therefore, you can quickly communicate with your machine through this software. Alright, so software usually looks like this boring thing. This is just a type. There are many different kinds of software. It depends on the company, what they use or they're using. Alright, software contain resolution selection. These are pretty default for almost any kind of software. Conversion between your two, again, system. So I graded your lab, and some of the students still not getting the unit. Give me like 0 units. So make sure you put inches. Most of them are inches in decimal inches, and also millimeters. So a lot of you are writing, forgetting the decimal. So we have 3 decimal, right? So don't forget the 0. Let's say like 1, 2, 5. Let's say we have like a 4 decimal place right there. Most of the instrument, totally, our lab have like 3 decimal, but for bigger machines, you have 4 or 6 all the way. So make sure you put the 0 before your decimal. Why this is so important? Because when you deal with a machine, you need this. Also in coding, you need this. And also in systematic writing for scientific knowledge, measurement, data, reports, transfer, you need this. So make sure you put that. Don't just give me like without this 0. I've corrected for everybody. You love to write this way, So you're not a high school student anymore, so make sure you pay attention to all the rules in the science world, okay? All right, and then we'll get into conversion axis. Conversions are rectangular coordinates to polar coordinates. So these are your middle school geometry, so make sure you get into it. Axis scaling, datum selection reset, circle center diameter solution, bold circle center diameter, save and recall previous data, nominal tolerance entry, out of tolerance computation. Anyway, so these are pretty much, okay, you can see in every CMM software that you can do or play with. Part programs. The computer is part of the manufacturing system, yeah. We heavily use it today, providing tremendous benefits to manufacturers, and everybody love it because it's so convenient and make our lives so easy. Program inspection prevents the operator's errors by fatigue, okay? It's just reducing the human error. The CMM part programs are easily generated by menu selection of CMM software right here. Operator just need, to click on an icon, so click. We all know how to use an application, how to use the software. So we can drive the probe sensor to collect data points from the workpiece in CMM part programs. So pretty convenient, huh? So the results are again shown with graphical image of part and measurements. So if you're starting 3D or if you're starting CNN, you should be able to have some sort of software in the class, and you should be familiar to your XYZ axis, okay? Pretty about the same thing that you can do, okay? Here's your geometries right there. The only thing that is different is this one is not linked to a inspection machine. We call it inspection machine. It's just your metrological machine. Okay, so therefore measurements can be programmed in CMM with a click of an icon. So the measurements performed frequently are created in library as automatic program steps or called subroutines. So here you can see your CMM icon right here. Pretty standard icon that you can be able to control the machine. And of course, you're hitting the measurement performed frequently. It's just a measurement you do every day, yeah? So we're going to create a library. This is your database anyway. And do automatic program steps. So you don't have to do it like every day. And your CMMs do it for you. Operator can then call up your subroutine by clicking the menu choice. We all know how to do it. Inspection programs can be developed from your, again, CAD models and then run in your virtual mode. So the image of the probe movement here, is used to optimize the probe path because you can see it. So we can eliminate, again, errors. We always talk about errors. Our goal is to eliminate errors, as much error as we can eliminate. So therefore we can get real precise measurement, yeah? And that's good for your product inspection and everything. But we want everything in our specification inspection and doing nothing but do we have everything right here in between this range right there, yeah? The first thing the quality assurance check is my data, is it within the range? That's all, yeah? And you have to do it like every day to make sure you are producing the quality products for the consumers. Okay, so here's a picture of perfection. It doesn't exist. Okay, nobody is perfect, nothing is perfect. None of the machines that we develop are perfect, but we just have to use it and make something good out of it. Okay, they only look perfect, but they always have some issue in there because it just, again, try to teach you, our important ideal. Ideal doesn't exist. Why? Because it doesn't have substance with it. As soon as you put the substance in your theoretical and ideal, okay, situation, perfection deviates, okay, from the ideal thing. So therefore, in inspection, a few points with best fit conditions are used. For example, only 3 points are input in the computer to establish, again, the center and the diameter of a circle. So we already know we need the one center in order to make a circle, right? It's not proportional because I'm drawing with my hand. So anyway, and then you're going to have 2 more points, one here and one there. So that way you can have your diameter and then your radius along with the first point, the second point, and the third point. Okay, and then you're going to use your compass and draw it one round. Yeah. Okay, so many CMM activities, they are repetitive. So therefore their calculations can be performed by computer. We will program it to do all these calculations we don't want to do. So these programs are known as your subroutines. Okay, so when you take a look at this table, we have multiple circle, we have multi-point sphere, we have multi-point cylinder, we have cone, okay, calculation, we have multi-point line, we have perpendicularity of 2 lines, and we have angle, point of intersection of 2, okay, coplanar lines. We have parallelism of 2 lines. We have parallelism of 2 planes. Okay, so anyway, these are different ways that you can measure your part, and we can program again our CMM to do all of the activities that we don't want to do. Okay, so it will calculate it for you automatically. However, more points again are better. Okay, when we're doing LET, I try to tell you about the points because a lot of us don't want to measure points. We try to measure this little border, remember? So I tell you how to do different points, more points. So you will get accurate profile. You only want to do like 5 points. That is pretty bad. Anyway, the more points you do, the better it is. It's because when a few points depart from the center, right, to some degrees, just depart meaning like again some deviations, so you will have error. Okay, you will have error in the center location and diameters. Like here in this example, we're dealing with a circle. Other useful subroutines are shown right here in this picture. So subroutines can be again prepared in CMM with a program, right, for any measurement required. So here, multi-point plane, we have 3D alignment, we have perpendicularity of a bar axis to a plane. Here, that's your bar axis right there. So anyway, you can read them in your own time. Operational modes. So let's get into big machine. So the operation modes are as follows. So we have manual, automatic, program, and we have stat mode. Yeah, stat is nothing but for the QA people. So we do the stat analysis. So the production line runs through the CMM, providing real-time inspection data. We call it stat analysis. They always say stat because it's pretty difficult to pronounce this thing when statistical and then making your tongue move. Okay. So anyway, so you will hear many people saying spec. Spec is for your SPEC. When we say spec, that means your lower limit and your upper limit. When we say stat, that's your statistical analysis. Okay, these are just common terms most of us use. Okay, so the production line right here, you can see your conveyor runs through the CMM. These are your machines providing the real-time inspection data that can be used to adjust the manufacturing processes. The machine center can be adjusted without leaving the machine idle, okay, during the inspection. So we just keep on running. So this is your pioneer for the metrology, and he is pretty cool, yeah, because all the manufacturers owe him for all the profits they made because of him, yeah. Make it easier for everyone. Metrological features, so CMM repeatability value decreases as the size of your CMM increases. The bigger the machine, the repeatability is going to go down. So they have exceptional repeatability and accuracy capabilities. Very reliable machines. CMM, they reduce computational errors. That's why we use it. High-speed CMM are inspection equipment because they can inspect the part as quick as they can, okay? So high-speed CMM are inspection equipment. They work on the shop floor. We use it all the time. Shop floor is just a floor that we do inspection for higher quality and faster throughput production. Again, every production quality matters. Speed, okay? We try to do it in our group lab, the very first one of the very bad. Anyway, so the tag time is all different, right? The operator 1, 2, 3, 4, you're supposed to have the same tag time, but we got all different. But that's okay. In manufacturing, what we're trying to hit is your product quality and then the faster throughput production. And we're going to use the CMM, okay? Continue with our metrological features. So CMM does not diminish the thermal errors because they are machine. So when we use them, we will definitely have a temperature of some sort. So every time you have a temperature of some sort, you have your thermal errors. Again, every time we think about thermal errors, they're a machine. When we run the machine, we run with electricity. So therefore, they generate heat. So these machines, they use a granite. Why do we use a granite? Because it's a poor conductor, right? To reduce the temperature anyway. Because granite is usually cool and doesn't release the heat build up quickly. So therefore, we choose the material granite. CMM structure and part measurement can be affected by thermal expansion. One thing better about manufacturing, like I see my very first job at Mohawk, I suffer heat. And then I suffer sound. Okay, so the sound and the heat. So you have your sound in manufacturing factory, and then your heat. Another thing is gonna hurt you. Okay, if you choose to do work in the manufacturing factories, and you get paid actually 3, 4, 5 times more than what I get paid here at school. Okay, school is the lowest you get. Anyway, you're not making any kind of money in academic. Therefore, people go outside to work because you need a house, right? You need to support your family, to feed your family every day. Also to make sure that they're okay after you die, whatever. So therefore, people go for high-paying jobs like that. Yeah, but then the downside is there's impact to your health, come from your sound, your heat, okay, and the noise. Anyway, so CMM structure, again, part measurement can be affected by thermal expansion. We all get affected, not only a machine, because you have like a gigantic machine all around you, right? And they're all running, so you suffer all of that around them. So thermal expansion is the amount of change in a part due to variation in temperature. And temperature changes is always happening in manufacturing world. That's why I try to teach you how to reduce the heat. So every 3 hours we have to go into the restroom, yeah, and wash not only hands. You have to wash your face, wash your neck, and then wash your eyes, your nose, and then your mouth. Okay, you have to do it all the time. That's one part of protecting yourself from all the dirt that we get from manufacturing floor. Okay. Also, you have to reduce the heat that you get from all these thermal expansion from your machine. Machine also again subjected to it, so therefore they have thermal errors. So it can cause by seasonal temperature changes, and that's your environmental, right? So environmental in your lab, if you remember, the environmental effect is again some student give me temperature, some student give me just dirt. So make sure you put all that, okay? All room conditions. So temperature changes, sunlight, heating, cooling, nearby machining operation, everything in the room is going to be your environmental condition. Transducers are used to measure the growth of X's due to the temperature changes. We use this to detect that this happened because of that, okay, growth of X's. So mathematical algorithm, okay, we can use them, then compensate for these temperature change as they occur, because you have to get rid of it. We cannot get rid of it physically easily, right? Therefore, you have to use adjustment, we call that. And we call this mathematical algorithm, mathematical adjustment, to adjust to get rid of this theoretically. Why? Because we can't do it physically. Yeah, everything that you have substance is really hard. Okay, and it's far away from the truth. So therefore, we have mathematics, we have algorithms, we have logic to correct these things. The temperature sensors, the incorporation of stable, low expansion materials such as invert reduce the effects of ambient temperature changes on the inspection process. Okay, so we correct the thermal errors not only physically on the floor, we also correct by using mathematics, and that is your key point to know. So some students might forget, I don't know if you have to learn this. Invert is not just material, and it's a nickel iron alloy. Okay, so we call that the iron is Fe, your periodic table, your nickel is Ni. Okay, and then we alloyed it, and then you give a number for that, so 36 is your invert. Yeah, so that's your iron nickel or nickel iron alloy. So we call ALLOY. So when you take industrial material, you will come to it. Anyway, we're all made of something. For human, it's CH and O mostly, and we have trace elements like zinc, nickel, calcium. For machine, most of them are metal, yeah, and they're not CHO, which is your organic. They're not organic. When people use the organic word, and it's just all misconception. Everything, your plants, okay, your animals, they're all organic. Doesn't matter, and you're dividing the plant into organic, but they are all organic. As long as you have CHO, it is organic. Okay, so it's kind of weird, grocery shopping term. Like, so scientists are like, what is this? Plants, every plant is organic. Doesn't matter what method you use, Anyway, so here, this thing is just showing you here the temperature sensors and the incorporation of your stable, low expansion material, right? And like I already showed you right there, invert, yeah? Because these materials reduce the effect of ambient temperature changes, especially in the inspection process. So here you have aluminum axis right there. These are just a scale, and this is the material invert. Yeah, and then here is the movement of a transducer. Again, transducer is going to be used, right? And we use the transducer right here to measure the growth of X's because of your temperature changes. So here is your movement of transducer right there, and we usually use a little bit of math right there. Delta, that's just telling you the change in D, another mathematical symbol, yeah. And here is a length correction value. You don't have to know this. And here C is nothing but your delta D, okay? And then I minus alpha invert divided by alpha aluminum. You don't have to worry about calculation here at all. All you have to know is just how the temperature thermal error, okay, is adjusted by using transducer and using a particular material. We call that invert. We can also use a substituted material here, anything that is going to reduce, all right, the heat is going to be used right there. Coordinate systems. So here are your x's right there, your z, your x, and then your y right here. So the coordinate system is just an address, right? It's telling you where the position of your part is. So this system allows your CMM to locate the feature on a workpiece relative to other features. So a coordinate system is like a 3D, right? It's just a map. So here I'm just going to underline this for you. We call that just an address. If you follow along that, you will be getting to the position that you target. So it gives the direction and then the location information. So here when you look at it here, they're going to Mark's World here. You have famous barbecue number 2, 4B, and then 7th floor. So that's just giving the direction to a location. So here in this example, it's just telling you if you're going to start from home right here, it's your 0 right there, yeah, in mathematics. So let's just go to 4B. So you know the 4 is right here, and then your B is right there. So therefore the location is right here, and it's said in this building it's going to be 7th floor. This is where starting is, yeah. Anyway, that's how we use a coordinate system. It's all about direction and location, so you can be able to find that location by following that instruction. Alright, so a manufactured part can also have a part coordinate system. Right now we're getting into manufactured part. So this is a little manufactured part, and it has a part coordinate system which identifies both the origin and your 3 axes for a workpiece. So here your XY plane is upper surface of part. Origin is lower right hand corner of part. Okay, so here lower right hand corner, that's your origin. Your XY is the upper surface of the part. Okay, so here is your upper surface. And X is aligned along the front edge of the part. So here is your front edge. It's going to be aligned in there, yeah? And here is your alignment right there. So the datum or features of the part define the origin and then your X, Y, Z axis for a workpiece. So right now, by reading the direction, you already know this one is Z, yeah? And then this is your 0 because that's your origin right there. And then it's an axis aligned along the front edge of the part. So therefore, this is your front edge. So that's your X. And then this is your Y right there. Okay, the process of alignment. Important thing in measurement again, alignment. So in machine is done by CMM measuring the part feature. Then first it's just telling you to do the measurement first and then calculate the part coordinate system, which is your X, Y, and Z, and then mathematically matching it to the machine coordinate system. Yeah, this is your measurement coordinate system, and you have another coordinate system which is completely programmed inside of your machine. So the alignment procedure matches the part coordinate system with the machine coordinates. So the alignment procedure here, what you do outside with the part, is going to match up with the coordinate system inside of your machine program. Okay. So without that, complex mathematical calculation must be performed to determine the offset, again, that's your deviation, from where your workpiece is in relation to the machine's origin. Okay, so you have anyway 2 systems going on, the one inside of your machine brain and the other one is the one that you're doing outside, and that needs to be matched up and got to have a smaller offset. Okay, alright, so CMM are usually calibrated. Every time we do calibration we have a standard, again standard prepared, and these standards are prepared especially for their CMM calibration. Okay, so we call it a CMM standard. So if we want to calibrate CMM, we're going to use the CMM standards. Every time you think about alignment, we're matching up, all right, the measurement coordinates and then the machine coordinates. So here the alignment procedure matches our coordinate system with the machine coordinate system. So here you can see two of them right there. And this is just a hypothetical matching, okay, procedure is trying to show you in the diagram. So without matching, we would need to perform complex mathematical calculations manually. Without the machine is a pain, right? And to determine the offset from where our workpiece again is in relation to the machine's origin. Anyway, don't get upset. Okay, you don't have to know everything here. All you need to know is every time we do the alignment, we are doing a match, and that is, okay, what are we matching? Part coordinates and the machine coordinates. So I'm going to underline that for you. This is what you have to know. That's it. Calibration, we use CMM standards. Yeah. You need it because it's a particular type of machine, so therefore you need particular standard to calibrate it. It's all common sense. Alright, portable arm coordinate measuring machine. So here you can see the little portable, and he is doing an inspection on this complex assembly, which is your automobile. You're going to take it to the workpiece. There's one assembly to do inspection. So this is your sample, and then this CMM is combined with a laser, right? He got a laser scanning tool, inspect the geometry of the car door surface right now. Aeroplane, the same thing. We need all of this surface pretty nice, huh? You don't want to produce a dented one. The customer's not going to buy from you. What is this? What is this? A joke or something? So we want all the surface to be as where it's supposed to be. So you have edges right there, and you have the different profiles right here. Trying to decorate the car so consumers are gonna love it. Yeah, so every detail that anyway need to be inspected. So again, what are you doing with this inspection? You're checking if all these measurements are within the range, okay, between your minus and your plus. Again, we call that tolerance zones. Yeah. So portable CMM can be, why is it portable? Because we want to pull it right everywhere we want to go. You can't put this thing into the machine. It's better to bring, right, the CMM to the part. Why? Because the part is big. So you can move around and then measure. So portable arm is very convenient. Why? Because it can be moved with you. Alright, future expectations. The next stage of our industrial revolution, okay, is your time and your children, grandchildren time, is going to go into interactive response. Okay, research starting from our generation, but we don't know how far it can go. So the current research interactive. Current research, IoTs, Internet of Things, want everything to be smart and connected and transparent, right? And then we're using heavy sensors, yeah. And then we're moving away from the world because the world is going to die into the space, right? Because endless energy right there. So therefore, we could be able to sustain, yeah. There's a hope that we can sustain human life. So anyway, all the machines are going. It got to be self-driving. It got to be self-maintaining. So everything that we say smart is because we need the machine to do, okay, repair by itself. So when you send all these probes to somewhere in the space, they can fix it by themselves. And we are going to program. So therefore, human can stay on our Earth right here and send all the automated machines out there to do our work so that we can get the energy that we need, yeah, and produce all the plant and animal we need. So another next generation Noah Ark again, yeah, in the future. Anyway, so those are the future expectations here. Interactive for metrology, the next step. So why do we have to do this kind of thing? Traditionally, we do something. After we do something, you don't just leave them alone. We analyze, yeah. We take a look at it. It's all right. And then we're going to modify if it's not working, yeah, the original process before we move on to the next step. So once we get everything perfect, or near perfect, I shouldn't say perfect, near perfect up to the point that we want to get, then we're going to move on to the next step. The future goal is to interface your CMM or CAD and CNC with the adapted computer control parts. Yeah. Alright, so I'm going to go ahead and stop right here. This is your last chapter. So you got to study on your final, yeah. And there are a lot, and make sure you go slow and study. And you have about 3 weeks in your hand, less than 3 weeks actually. So make sure you study, use your time, okay, drinking alcohol and going to the bar, going to restaurant that need to be reduced. Relationship, okay, everyone needs family, put that aside for a while. There's 2 weeks, and please study and hit the final, yeah. And then you can do all of that after a final in winter break, okay. All right.